In this discussion, we delve into EarthPT, a specialized model for processing Earth observation data. This model is designed as a pre-trained transformer that operates with 700 million parameters. It's trained in an autoregressive and self-supervised way, which means it predicts future data based on the patterns it learned from past information. Notably, EarthPT excels at forecasting pixel-level surface reflectances across a wide spectral range from 400 to 2,300 nanometers. For instance, when predicting the normalized difference vegetation index, it exhibits minimal error and outperforms basic models that rely solely on historical data. Moreover, the embeddings created by EarthPT are rich in meaningful information, which can be utilized for detailed tasks like land use classification. The vast amount of Earth observation data available means there's a significant potential for expanding EarthPT's capabilities without data limitations. Methods. This section is dedicated to explaining the methodologies employed in this research, focusing on the datasets utilized for training the EarthPT model, as well as the associated hyperparameters and training procedures for the chosen transformer architecture. Training imagery. The core algorithm under consideration is ClearSky, a sophisticated deep learning framework designed to predict imagery akin to the products generated by the European Space Agency's Sentinel-2 across 10 distinct spectral bands, which include blue, green, red edge bands 1 to 4, near-infrared, NIR, and shortwave infrared, SWHR, bands 1 and 2. The input for this predictive process is provided by Sentinel-1 C-band synthetic aperture radar, SAR, imagery notable for its resolution of 10 meters per pixel. A crucial advantage of SAR imagery is its ability to operate seamlessly through cloud cover, which is a common issue in optical imagery, thereby enabling the ClearSky algorithm to create uninterrupted multispectral imagery over time. For this study, the researchers focused on a specific region in the UK, defined as a 100 square kilometre area aligned with the TL square of the British National Grid (BNG) reference system. The dataset comprises time series for both training and validation, covering a period from January 2015 to December 2022. Additionally, a test set is established, ranging from January 2023 to May 2023. Data points in these time series are collected according to the observational schedule of Sentinel-1, which typically results in observations every 5 days in this region. Pre-processing. Prior to utilizing the data in the model, pre-processing steps are undertaken to organize the beneficial information systematically. The observation arrays are transformed into a structured format using float 16-number PY arrays, configured with 3 dimensions. The first dimension represents a flattened spatial index corresponding to a 10 by 10 square kilometer BNG tile. The second dimension indicates the date of observation, and the third dimension encapsulates the individual spectral bands alongside date embeddings for both the current and subsequent observations. To incorporate the date into the analysis, a mathematical embedding is computed using the equation that generates sine and cosine components of the date, ensuring a continuous representation of the time variable. Specifically, the equation is framed as the sine and cosine of /2/pi/ multiplied by the day of the year divided by 365, where t denotes the day count since January 1st of the current year. Furthermore, the reflectance values from the spectral bands, which initially range from 0 to 10,000, undergo normalization into a range approximately between -1 and 1, achieved using the formula \hat v equals \frac v 500s1 \. These transformations are essential for preparing the input data to ensure it is suitable for training the model effectively. In this segment of the method section, we delve into the mechanics of the EarthPT model, particularly regarding data handling and the transformative architecture that underpins its functionality. Data preparation. The authors treat each time-based observation as a discrete token, resulting in a training dataset of approximately 100 billion tokens drawn from the entire UK dataset. This substantial size allows for robust and comprehensive training. They leverage memory mapping techniques to efficiently access the data during training, which optimizes the process of utilizing large datasets. Transformer architecture. EarthPT operates on an autoregressive transformer architecture, a model type well known for its capability in sequential data processing. While built on the foundation laid by Radford et al., the authors adapted the architecture for their unique, non-textual dataset. Instead of employing a standard word embedding mechanism, they utilize a multilayer perceptron for embedding the input data. This approach ensures that the input data aligns in dimensionality with a designated time embedding vector. To effectively integrate the temporal context of observations, the model is supplied with two floating point embeddings, one for the date of the current observation and one for the subsequent observation. This inclusion is critical as it enables the model to learn patterns over time effectively. Training follows a conventional autoregressive method, where the model strives to predict the next observation in a time series, continually refining its predictions. The training employs the Atom Optimizer, known for its efficiency in handling large datasets, alongside the Huber loss function, which mitigates the impact of outliers during training. Multiple models with varying sizes, from 10 million to 700 million trainable parameters, were trained, while the details related to hyperparameters for these models are provided in Appendix B. Notably, the paper proceeds to focus primarily on the largest variant, EarthPT 700M. To determine the optimal dataset size for effective training, the authors reference the chinchilla neural scaling law. This law posits that for a decoding transformer model, the relationship between the number of parameters, denoted as n, and tokens in the training set, d, follows a scaling rule of approximately 20 times d for optimal compute efficiency. Thus, for a model with 700 million parameters, they conclude that about 14 billion tokens should be deployed, leading them to structure their training accordingly. Training process. EarthPT 700M is trained on 8 A100 PCIe 40 GB GPUs, with a total of 90,000 training steps, processing 160,000 tokens per step. This extensive training schedule sums up to about 560 A100 hours of computational effort. This methodical setup not only outlines how the authors prepared their dataset and established their model architecture, but also sets the stage for the forthcoming experiment section, where the applications and implications of EarthPT can be anticipated. In the results section, an assessment of the EarthPT model's performance in forecasting remote sensing data is presented. The experiments primarily focus on the model's predictions of four key indices: Normalized Difference Vegetation Index, NDVI, Normalized Difference Water Index, NDWI, Bare Soil Index, BSI, and Green Chlorophyll Vegetation Index, GCVI. Figure 1 illustrates the model's forecasts for a specific pixel from the UK national grid, conditioning EarthPT on a historical time series spanning 8 years. This generates long-term forecasts that are subsequently compared against actual observed values post-forecasting. Figure 2 provides a quantitative measure of model performance by displaying the median L1 error, essentially a measure of the average magnitude of errors, in the NDVI prediction across approximately 1 million pixels for the TL63 tile. The results reveal that EarthPT achieves a median L1 error of 0.05, outperforming a phase-folded baseline model, which returns an error of 0.08. Given that NDVI values range from -1 to 1, this indicates a notable accuracy for EarthPT's predictions. In practical terms, this level of performance is significant in applications such as predicting drought conditions, thus offering actionable insights from the data. These findings are critical, as they not only validate EarthPT's capability to forecast remote sensing data, but also establish a foundation for its potential use in broader geospatial analyses. By leveraging the model's predictive strength, researchers can envision its extension to land cover classification through the generation of representation embeddings. Figure 3 visually demonstrates how pixel time series embeddings can be clustered and analyzed, allowing for the creation of a dynamic land cover classifier based on semantically meaningful labels. This would enhance the model's utility across various sectors, indicating a profound impact from improved forecasting methods in remote sensing data interpretation. Overall, these results underscore the effectiveness of the EarthPT model in achieving reliable, forward-looking analyses crucial for addressing environmental challenges, setting the stage for subsequent discussions in the future work section. In this conclusion section, the research highlights the development of the EarthPT Large Observation Model, inspired by the growing interest in large language models, LLMs. This innovative foundation model excels in forecasting surface-level optical reflectance, allowing predictions months into the future at pixel resolution. Furthermore, EarthPT generates informative embeddings from input time series, which hold potential for applications such as land cover classification. The paper underscores the vast data availability, with approximately 10 to the power of 15 tokens accessible, suggesting scalable improvements in model performance if neural scaling laws are validated. These advancements exemplify a significant step forward in Earth observation technologies. Ongoing R&D efforts will continue to enhance EarthPT's capabilities. The model's code and weights are readily accessible for further research, indicating a commitment to open scientific collaboration. This conclusive overview encapsulates the substantial contributions and future directions in the realm of remote sensing and machine learning.